we're gradually getting into doing chemistry. We know our symbols, we know how to name compounds. Now we're going to talk about chemical reactions and stoichiometry. Stoichiometry is a fancy name for just keeping track of what goes into a reaction so you know what comes out of the reaction. The word itself comes from a root, which means countable. So you're counting things that go in. The reactants go in, the products come out. And you can theoretically determine how much product you will get from a known amount of reactant. I'll let you read that on your own. But like I said at the very beginning, these things are happening at the microscopic level. So in addition to developing sort of an intuition of what's going on down there, we've got to be able to actually quantify what's going on at the microscopic level. So we use a process called counting by weighing. We understand now, ever since Dalton's atomic theory became accepted, that what guides a reaction is the number of atoms that go into a reaction and the number that come out, not the mass. But we don't count numbers of atoms. Right? They're too small. There are too many of them. So you take a supercomputer just to do a simple benchtop reaction. So we use the next best thing. If you know how much each atom weighs on average, then you can weigh what you have and determine approximately, actually pretty close, how many atoms that represents or how many molecules that represents. So that's the concept behind counting by weighing. We use the macroscopic here to determine the microscopic there. Okay, example. I already said that. Well, we do need, all right, it bears repeating. We know atoms are too small to count, but actually not just too small to count, we can do that, but just too many of them to count. Objects behave as though they were all identical. That's required. Whether it's atoms or molecules, if you have a molecule of water, that all the water molecules behave as if they were identical, especially in mass. And then you need some way to determine the average mass of the object. So how do you do that? Well, our example is marbles. All right. So you have a jar of marbles and you weigh however many marbles you have, you weigh them and say they come out to that mass. Well, you could go in and count them all, but we're trying to extend this analogy to atoms, and that wouldn't be fair, just counting them. So we take 10 of them and we determine the mass of the 10. Why do we do that? Because of this previous requirement. You need the average mass of each object. Once you know the average mass of each object, then you can use dimensional analysis to determine how many of the marbles there are in that pile. Right? So if we want to know what's the average mass of the marbles, we know 10 of them weigh this. Right? Does that look familiar? It's a conversion factor. This many marbles equals that mass. So you can use that to convert one unit to another. We want to convert this unit here to numbers of marbles. Now, the way the author set it up and the way the slide presents it, you first have to find the average mass. You don't have to do that. You can, I mean, it's valid. That would tell you how much each marble weighs, 3.760 grams per marble, which is okay. But you don't have to do that. This is your conversion factor. So if you have 394.80 grams, you need a conversion factor that will cancel grams and leave you with marbles, right? Like that, like that. And this is where we're headed. So we know that 10 of these marbles are worth this value. And there you have it. That's all you need. Right? Dimensional analysis at your service. Like I said earlier, lots of chemical problems can be solved by just unit conversions. This is one of those occasions. All right. So the example here is presented as you find the average mass of the marble. Now, this is good information because we're actually going to do that for individual atoms. How much does an individual atom weigh, or what's its mass? But I just wanted to make the point that when it's presented this way, you don't have to do that intermediate calculation. But the intermediate calculation has already been done for us. And it's right up here on your periodic table. Underneath every one of these is the average mass of the atom for that element. It's called the atomic mass. We're going to use that eventually. But in this case, if we solve this problem either this way or that way, you can estimate that you have 105 marbles in that pile. All right. Make sure I'm still recording. Well, how do we count the number of atoms in a pile? Well, we need a standard. We need something that everybody agrees upon. Used to be oxygen. Used to be one isotope of oxygen. That one. The problem with oxygen is it's difficult to obtain pure samples with even advanced equipment because you're dealing with a gas. And because oxygen also exists in nature as a diatomic, it's not going to be like that. It's going to be like this. And that kind of screws things up. So eventually, the international community settled on a different standard. They chose carbon. Carbon-12 isotope, which is the most common isotope of carbon, shouldn't be difficult to purify. And in its pure form, it's a solid. Okay. So we settle on carbon. And what we're saying is this isotope of carbon is given that value, 12, as many decimals as you want, atomic mass units. Now, what is an atomic mass unit? Well, it's pretty close to the mass of the proton. But whatever it is, carbon has 12 of them, exactly 12. And it's the only isotope that has exactly 12. Now, I know what you're thinking. We learned all that stuff about isotopes, right? Add the protons and neutrons together and you get the mass number. Well, now it's not just the mass number we're talking about for this isotope. It's the actual mass. Not the numbers of protons plus neutrons, but the atomic mass units that we're assigning to that isotope. And everything else is compared to that. That's why no other isotope will have exactly a whole number there. with infinite decimals. The rest of them are fractional. Okay? Take my word for it. Okay. Okay. So we're eventually, what we're going to do is we're going to take that standard and we're going to use Avogadro's law to compare equal numbers of atoms. That's where Avogadro's law really comes into its own. Because if you can't compare, if you don't know you have exactly the same number of atoms of one element versus another, you can't compare their weights. Right? You remember Avogadro's law? It bears repeating. He said if you have a volume here, of two gases, no matter what they are, and the volumes are equal. Also, the temperatures are equal. And the pressures are equal inside these spheres. If all those three are equal, then you know that the number of atoms or the number of particles in this one is equal to the number of particles in that. So now, all you have to do is convert carbon to a gas, which takes some doing, but can be done. And then you have carbon in this one, and you have anything else in this one, oxygen, for instance. And you have to have monatomic oxygen here also. Or you have to recognize that oxygen is diatomic. And then if it's diatomic, then you can make the conversion so that you know that one atom is worth a certain amount rather than two, which is part of the determination. So if this one is 12, this one's going to be approximately 32 point something. So one of them will be half of that, right? And all you have to do is compare a few gases with this one. And once you've got the comparison established pretty well with 6 or 7 or 8 decimal points with other elements, then you can start comparing more convenient sources with your new elements rather than going all the way back to carbon. I'm sure that's how they do it. Okay, so that's how Avogadro's number makes this standard usable. That's saying Avogadro's number, Avogadro's law. We haven't talked about Avogadro's number yet. We will. So there's your standard. They abbreviate with just a U. I like AMU, sort of, because sometimes you can get this one confused with this one. That's U, that's atomic mass units, and this is mu, the abbreviation for micro. Sometimes you can get them confused. So I like AMU. I've already said that. Now, what we have to recognize also is that isotopes in nature occur in mixtures. Most of them have one dominant isotope, and it's going to be the stable one, except when you get really, really heavy atoms. And then all of them could be radioactive. But for the lighter ones and the ones that we're more interested in, there's going to be one that's predominant. It's the dominant one of the isotopes, except for some exceptions. Chlorine is one of them. Chlorine has almost evenly split between two isotopes. The, let's see, 17 and, let's see, no, that's 17, 34 and 35. It must be 36. Maybe 35 and 36. Anyway, the two major isotopes in chlorine are almost equal in abundance, but most of them there's one isotope that dominates. What do we do with that? I mean, if we can determine the atomic mass relative to carbon of individual isotopes, then how does that help us, right? Because most chemistry labs are not equipped to separate isotopes and do chemistry. We work with what we've got, the mixtures. So we need a value, an atomic mass value for naturally occurring elements, which includes their mixture of isotopes. So fortunately, that's the way the table's set up. Those values right there, they're not individual isotopes. They're weighted average values for all the naturally occurring isotopes for that element. That's why periodically they're updated. New determinations with more accuracy and precision are developed, and those values now are substituted in a new issuance of a periodic table. Fortunately for us, they never change in the second decimal place. So that's why I round to 2 decimals and we're finding good to go on 30-year-old table. But if your research requires 6, 7, 8 decimal points accuracy, and it could impact the outcome of your experiments. But for us, no. We just know it happens, and that's good enough. Okay, what about this mixture of isotopes? Well, like I said, carbon is predominantly carbon-12. It's 98.89%. But there's also carbon-13, which is only a little over 1%. But it's enough to influence the average value that you'll see up here on the table. There are some other isotopes, but they're insignificant. In fact, carbon-14 is radioactive. Fortunately, it's less than 0.1%, so we can virtually ignore it. Okay, so how do we determine this weighted average? Well, if you've ever manually calculated your grade point average, then you know what a weighted average means. Some grades are more heavily weighted than others. Right? Like this class is 3 credit hours, the lab is 1 credit hour. So if you get a B in this class and an A in the lab, then the B is going to have 3 times as much weight as the one in the lab. You know what I mean? It's a weighted average. So what we do for our elements is we incorporate this. We say the average atom, right, which doesn't exist, but it's a way to think about the carbon atom in this case. The average atom is composed of 0.9889 fraction of 12 atomic mass units. Right? That's what its contribution is. I was using the decimal equivalent of percent. And this isotope, which is not a whole number, there you go, because it's compared to this parent value, is 0.0111 fraction of that value. Right? So this is going to be a major contributor, and this is going to be a very, very minor contributor to the average mass of the average atom. And when you multiply these out and add them together, you end up with something in the neighborhood of 12.01, rounded off to 2 decimal places. We could round it off to more decimal places because this is an exact number. It doesn't matter, right? But this is, well, actually, this does matter. It's 2 decimal places. No, wait a minute. It's 4 decimal places. Or 3 significant figures. So that's what we use for the natural mixture of carbon in nature. We don't use 12, we use 12.01 because it's going to have a little bit of that in it. Okay? And that's what every number right up here represents that average atom value. You're not going to find an atom with exactly that mass ever in nature, because this represents the weighted average for that element. Okay, any questions? Well, I'll take a sip. Okay. Now you're probably wondering, some of you maybe, what good is atomic mass units? How are we going to use those? I mean, you could do them for individual atoms, maybe for groups of atoms. But what good is that when you go in the lab, right? We don't have any scales in the lab that'll measure atomic mass units, do we? Not in my lab, we don't. Never have had. So this needs to mean something else. And we're eventually going to get there. This just reiterates the point. Even though naturally occurring carbon contains atoms that are on average this mass, you won't find a single atom that is that mass. Does not exist. It's a weighted average. Okay. But it does allow us to count the number of atoms by weighing them. Except my balance doesn't read atomic mass units. So we need something else. Oh, we got a pretty picture though. How do we know the natural abundance of isotopes? Well, if your lab's got enough money and you have the need, then you can use a mass spectrometer, which essentially separates those isotopes and counts them. With the fast electronics these days, these detectors can count individual atom strikes on the detector. And it does so fast that you could probably count up the number of atoms of reaction products if you wanted. But that's not what this is used for. What you have to do is you take your sample, which is as pure as you can get it, naturally occurring element, right, with the isotopes mixed in. And then you ionize them, right, because you have no control over neutral atoms. Right? They do not respond to electric fields. They do not respond to magnetic fields. Only ions in motion will respond to those fields. So we use those. Once we've ionized the atoms, and each atom has the same charge, that means the influence of the magnetic field here will be an equal force, because the force is based upon the strength of the magnetic field and the charge. It doesn't matter what the mass of the atom is. So the same force is applied to every atom here. But before we get there, if you don't have a straight beam, then how do you know which strike belongs to which isotope? You don't. You need a straight beam. And this is really too broad. It's a lot narrower than that. You just use two parallel slits. And let's see, did I mention that with Rutherford's experiment, collimating a beam? Yeah, that's what you're doing here. You collimate the beam. So the only ones that can get through both of them are the ones that are flying in a straight line. So now that they're flying in a straight line, when they go through this magnetic sector, the same force is applied. Remember, force applied to a larger mass moves it less. Let's just put it that way. So the heavier ones are going to land way out here. They bend less. And the lighter ones are going to end up over here. And that's how you count them. And you can count the relative abundance of isotopes that way. Okay. So what's the average mass of this one? if you have 62.6% of this isotope and 37.4% of this isotope, then what's the average atomic mass? You just do that weighted average thing, right? When it says percent, I use the fractional equivalent. It saves a lot of calculation. So 186.956 atomic mass units times what percent? 62.6%. Right, that equals a value. That's its weight contribution. And the other one, 184.953, is lesser, 3740. Okay. Whatever that is, add it up. Okay, and when we do that, we get 186.2 atomic mass units. Now, can we identify the element from that? That's not the atomic number, right? Atomic number would be definitive, nothing else but an element. But the way the table is arranged, it's not only arranged in order of atomic number. In fact, originally, Mendeleev arranged it by mass. They didn't know about atomic numbers. So from upper left to lower right, well, from left to right and top to bottom, you increase. So all you have to do is follow along. Just follow along here, right? There's 69.7, getting bigger, 70, 83. Keep going. What are we heading for? 186, 131 xenon, and 100, whoa, wait a minute, almost too far. 186.2071 is rhenium. So you can use the mass to find an element as well. You don't always need a number. Now, it can get tricky because some of these masses are really close together. I should have checked it out to see. Right, here's one that's really close. Tellurium and iodine. Iodine is 126.9 and tellurium is 127.6. That's one of the situations that Mendeleev ran across, right? They should be increasing in mass, but he found that iodine was a little bit lesser mass than tellurium, but iodine didn't fit with the chalcogens, and tellurium didn't fit with the halogens in their chemical and physical properties. So he switched them. He said, that's more important. And turns out he was right. But you can use the atomic mass to get pretty close. And then you would need, in cases like that, you get a tiebreaker. Okay, let's see. There it is, rhenium. You didn't have to memorize that one. Okay. So now we're gonna, I don't know what the right word is. We're gonna make a usable value out of that atomic mass unit. The atomic mass unit doesn't only mean atomic mass units per atom. If you have a certain number of those atoms, and that's a specific number, the mole. If you have a mole of those atoms, then that same value is equal to grams. Right? And mole has to be a huge number. In fact, it's named Avogadro's number. He didn't determine it. They just stuck his name on it to give him credit for getting the ball rolling. So the mole is actually a number of things, any number of things. For us, the most important number of things is atoms and molecules and ions. But you could speak of mole in terms of, I don't know, basketballs or chickens, anything. You can have a mole of anything. But for our purposes, it's the number equal to the number of carbon atoms in 12 grams of pure carbon-12 isotope. That's the definition. And they use that definition to experimentally determine the value of the mole. Now we're going to round it off. For our purposes, that's good enough. That's the one we're going to use, 6.022 times 10 to the 23rd. And that's Avogadro's number. And this is the number of, well, by definition, the number atoms of carbon 12 is equal to 1 mole. But it could be anything. When you say it's this many atoms of that one, then we can also say that many grams. Okay. So now the periodic table becomes more useful. Because if we have a sample of aluminum, and we're able accurately to measure 26.98, that's good enough, 26.98 grams of aluminum, pure aluminum. We have that many atoms of it. All right. But naturally occurring carbon, right? If you don't have this isotope, you get naturally occurring, just take that off. Naturally occurring, you would need 12.01 grams because you got mixed in with it some carbon-13. Okay. Let's see. Calculate the number of iron atoms in 4.48 moles sample of iron. Now, we're going back to dimensional analysis. 4.48 moles, you want to convert that to number of atoms. This is where you're starting, and this is where you're ending. So how do you get there? You want to end up with atoms, and you want to get rid of moles. So whenever you see that relationship, numbers of something, atoms, molecules, ions, and mole as a quotient, you know it's Avogadro's number. And that will be 2.7 times 10 to the 24th. Is that reasonable? Right. What's 4 times 6? 24. And then a half again as much. 24 and 3 is 27. 27 times 10 to the 23rd, which means 2.7 times 10 to the 24th. So yeah, it's reasonable. Do a quick estimation in your head. All right. So for nitrogen, you look it up in the periodic table. That average molar mass of, that's what this is called, molar mass, because it's the mass of a mole. Molar mass of nitrogen is 14.01, rounded off 2 decimal places. How would we do it for a molecule? It's very simple. If you have a mole of this molecule here, if you have 1 mole of that, how many moles of oxygen do you have? You have 1 mole of oxygen atoms. How many moles of hydrogen atoms do you have? 2 moles of hydrogen atoms in that molecule, right? So now that you know each one of those, all you need is 1 times, what's the value for oxygen? Well, it's 16.00 grams per mole. How about hydrogen? 1.01 grams per mole. So this would be 2.02 plus 16 is 18.02. Grams per mole of water. So all you have to do is, once you've got the formula, you just take the individual molar masses for each of the elements times how many of them there are and add them all together. And that's the molar mass for the molecule or the formula, right? If it's not a molecule, say it's table salt, right? Sodium chloride is not a molecule. It's a crystal lattice. But for the formula, NaCl is 1 sodium and 1 chlorine. Add them together, and that's the molar mass of NaCl. 1 of each. We'll do another example. There we go. How about this one? That's a big one. Barium. Where's barium? It's an alkaline earth. So it's going to be over here, way down there. 137.2.33. 137.33. You got one of them, right? Nitrogen's 14.01. We saw that earlier, times 2, because it's got this subscript. You got 2 nitrogens in there. You got 2 nitrates, which means 2 nitrogens and 6 oxygens. So 6 oxygens, 2 nitrogens, and 1 barium gives you that molar mass for this formula. Okay? That's how you do molar mass for a compound. So earlier when I was pushing, learn how to name these compounds, learn their formulas, how to write formulas. I was just playing around. You're going to need that. If you can't do that, then you're going to have a lot of trouble. Okay, which of the following is closest to the average mass of 1 atom of copper? This is kind of a dumb slide. If you think about it, is 1 atom of copper ever going to weigh so many grams? No, it's going to be a fraction of a gram. But we can calculate that. I think the slide does it for us. Let's see. There we go. So you're converting 1 copper atom to grams. But we don't know how much 1 copper atom weighs in grams. We know atomic mass units. But that's not going to help us answer the question, because we want to know the average mass of 1 atom of copper. And we probably should have said the average mass in grams. So 1 copper atom, we can convert that to moles, right? 1 mole is this many copper atoms, right? That's a divider right there. So this is in the denominator and this is in the numerator. So now we're going to have that many moles. Well, what's the mass of a mole? 63.55 grams of copper per mole. That cancels the moles and leaves you with grams. And we got it from right here. 63.55, rounded off to 2 decimal places. And there you go. That's the mass of 1 copper atom on average, because we don't know what the isotope is. That's the average mass of 1 atom of copper, the weighted average based upon the naturally occurring abundance of its isotopes. Right, this one should be fairly easy. You don't have to calculate this one. Well, what's the number of copper atoms in 63.55 gram sample of copper? That's 1 mole, isn't it? So it's 6.022 times 10 to the 23rd copper atoms. trick question. Okay. Now we get a little more complicated. Let me see, how am I doing on time? 125. So I got 20 minutes. We're probably going to run over. We'll use up some lab time for this, and then we'll talk about next week's lab. We need to discuss that before you get away. Which of the following 100-gram samples contains the greatest number of atoms? We can actually solve this without doing calculations also. It's conceptual. If every one of these samples is 100 grams, how do you end up with that many grams? By the individual mass of each atom, right? You have enough of them to make up 100 grams. So if I've got a bag of jelly beans over here, and I've got a bag of lead shot over here of the same size, and I want the same mass of each one, which one do I need more of? Jelly beans, because they're lighter for each one. Same concept for atoms. The one that's going to have the greatest number of atoms is the one that has the lightest atom on average. So you just look it up in the table, right? Silver is the heaviest, then zinc, magnesium is the lightest. So magnesium will require more atoms to make up 100 grams. Okay? Now we'll get a little more complicated. If we have this, we've got magnesium, zinc, and silver again. Right, so we have 107.9 grams of silver and 70 grams of zinc and 21 grams of magnesium. Now, which one, we want to rank these in order of greatest to least. And if I hadn't said it before, when you're ranking something, when you put things in order, I always nail down the ends. But it's not that difficult here because we're looking for the number of atoms. And if you look at the numbers and compare them to their molar masses with only 3 values, we should be able to order them really quickly. 107.9 grams of silver. What's its molar mass? Let's see, 107.9. So this is equal to what? 1 molar. How about zinc? 70 grams. Let's do that right. 70.0 grams of silver, zinc is greater than a mole, right? 65.8 would be a mole. So this is greater than a mole. How about 21 grams of magnesium? Well, magnesium is 24.3. So this is less than a mole. So now we can put them in order. This one's in the middle. And greatest to least. So the greatest would be greater than a mole, which is B. A is silver. And magnesium is the least. Okay, BAC. Okay. So this is a perfect place where you can overthink something and have to go dig into your bag of tricks and say, oh, I've got to calculate exactly how much of each one there is. No, you don't. Not if you just put them in order. You only need the relative amounts of each one. If you think like that, then maybe your test will take 45 minutes instead of 2 hours. But you have to know what you're doing. That's the key. You have to know it, and you have to know you know it. And the best way to do that is to work as many problems as you can get your hands on, and as you have time for. The more, the merrier. All right. So now let's say we have 100-gram sample of each of the following. Water, dinitrogen monoxide, right, type 3 compound. You won't know what this one is. That's propionic acid. And carbon dioxide. Rank them from greatest to least number of oxygen atoms. When you have a problem like this, recognize that you're going to be doing the same type of calculation for every one. You just change minor conversion factors to get there. So I use Henry Ford, right? How did Henry Ford, what was his claim to fame? The assembly line. He made cars the same way over and over and over again. That's how he could make them so cheap. And originally he said you can have any color you want as long as it's black. Okay, so I set it up like this. Water, nitrogen, dinitrogen monoxide, H6, O2, propionic acid, and CO2. Okay. Now, what do we need to know? 100 grams is where we're starting. So each one is 100 grams. Okay. Assembly line. Now we're going to convert that to what? Number of oxygen atoms. Can we do it directly? There's no conversion factor to go directly. So this is going to be a chain conversion. You're going to make a couple of steps before you get there. We're going to convert grams into moles of molecules. All right. So we got to get rid of grams in the denominator, and they'll leave us with a mole of whatever, a mole of the molecules. So we need the molar mass of each one of these. Right, we did water already. It's 18.02. Dinitrogen monoxide. What's that? Well, let's see, it's 2 times 14.01 for nitrogen and 16 for oxygen. Right. So here's where you have to know how to work your calculator. Let's see. I'm going to say 16, and then I'm going to say, do that one in my head, 28.02. So that's 44.02 for this one. Right. This one's going to take a little more work. 3 times carbon. 3 times 12.01 for carbon. Hydrogen. 6 times 1.01. Look it up, see if I'm right. 1.01 for hydrogen and 2 for oxygen. Rounded off to 2 places. Okay. So 3 times 12.01 is 3603. And then 6.06 for hydrogen, and then 32 for oxygen. So that's 74.09. Okay. How about carbon dioxide? Well, you've only got 1 carbon, so that's 12.01, and 2 oxygens, which is 32. So that's 44.01. So carbon dioxide and dinitrogen monoxide are almost the same molar mass. Okay, so now we've got moles of compound. Now we need to find out moles of oxygen atoms. Do we actually have to determine the number of atoms? Do we need Avogadro's number? Not if we're going to put them in order, because the mole is a counting number. If you know the number of moles of oxygen atoms for each one, then you don't need the absolute amount of oxygen atoms. You just need to know the moles of oxygen. It's kind of like using scientific notation. No, it's a small unit. It's a large unit, so you can use small numbers. All right, so let's convert the number of moles of molecules. Right? So for every 1 mole of the molecule, how many moles of oxygen? Well, for this one, we've got 1 mole of oxygen for every mole. Right? 1 to 1. How about this one? Still 1 to 1. 1 mole of oxygen for every mole of the molecule. This one, you've got 2 oxygens for every mole. And this one, you have 2 oxygens for every mole. Okay? So now, let's see. Have we got everything covered? Cancel, 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 cancel. Okay? And cancel, 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 cancel. And what are we left with? Moles of oxygen. That's the thinking part. That's the hard part. Now it's just number crunch. So I'm not going to crunch numbers. If you do those calculations, and in my calculator, I say 100 times 1 times 1 divided by 18.02 divided by 1. In that sequence. 100 times 1 times 1 divided by 40.02 divided by 1. Or 100 times 1 times 2 divided by 74.09 divided by 1. That's the way it goes into my calculator. Now, yours being algebraic, maybe what you can say is 100. Well, in this one, 100 divided by 18.02, that's it. How about this one? 100 times 2 equals. And then divide by this one equals. That's the way an algebraic calculator works. Or you might be able to put in a sequence of operations. I think you can. As long as there's no parentheses involved. You can say 100 divided by 74.09 times 2 equals. I think they work that way now. Okay, but when you do that, you find out that water, 100 grams of water has the most number of oxygen atoms. Does that make sense? Well, yeah. If they're all equal mass, water is virtually no hydrogen. It's virtually all oxygen. So it makes a whole lot of sense. Okay. Anybody have any questions about that? About Henry Ford? Henry Ford was human. He came up with the assembly line. And well, I don't know if he invented it, but he commercialized it. And besides the fact that he was a rabid racist and anti-Semite, I mean, he still made good cars. And he was rotten to his son. Anyway, so this is just a conceptual description of how you solve a problem, right? This first one means, what's the question? Right? Take time to read the question. It'll keep you out of a lot of trouble if you understand what the question is. And then figure out a roadmap, plot your path to an answer. And then look in the problem, is all the information I need there? Or do I need to go look someplace else? Right? Do I need to go to the periodic table, for instance? Or do I need to go to those useful information things that I give you for free? You know, what do you need? Right? This is critical thinking. Right? We're not plug and play here. there are methods, of course, for helping us get to the answer. But just because we've been studying a certain problem solution doesn't mean that a problem pops up on the test that you can use just what you studied in that chapter. You studied lots of stuff in previous chapters that may be applicable to solving the problem. So don't forget that stuff. And then check yourself. Does this answer make sense? I don't know if I told you about this. I had a friend when I was a graduate student and a research associate at Louisiana State University. I lived in an apartment complex, and one of my neighbors was a mechanical engineering student. So I had some pretty complicated mathematical problems to work out. He said he was amazed at the number of students in his classes that would be given a problem on an exam or a problem just for homework. And they would think to themselves, we've been studying this type of problem, so we're given these numbers. We're going to shoehorn these numbers into that calculation and get the right answer. It doesn't work that way. They said they would come up with answers that were supposed to be in the neighborhood of, 20 or 30 newtons of force. And their answers would be 25 million newtons. And they would just put it down on the test because they didn't know any different. They kind of lost the capacity to think or never developed it in the first place. So it was just amazing. And of course, those students fell by the wayside. Only the ones who actually thought, used their brains, were going to pass the course. Okay. How do we express, right? We sort of led into this with an understanding that the periodic table, when we were discussing atomic mass units, wasn't very useful, not for us. We needed that relationship of mass to molar, that molar mass relationship that gets the ball rolling. But when you go in the lab, you don't even do that analysis. Usually, if you're going to ask yourself how much of an element is in this mixture, you're going to come up with a mass percent. Right? There's so much mass of this element in this, say, ore, for instance, so much iron in this sample of ore on a percentage basis. So what do we mean by that? Well, you know the mass of the element by your analysis, and then you know the mass either of the compound or of the sample, whatever the case may be, the total mass divided into that mass times 100 is the mass percent. Now, when we're talking about mass percent for compounds or formula units, you want to know what's the mass of the compound. And here you can visualize this as molar mass of the compound. And in 1 mole of compound, you have a certain mass. And in 1 mole of that compound, how much of that element is in there? Then you ratio those two. So the mass of the element ratio to the mass of the compound times 100 is the mass percent. Now you can do that experimentally in the lab. If you have a purified compound, then you can determine the individual elements in it and their relative masses expressed this way. Or you can do a theoretical calculation based upon the formula unit of the compound. And that's what we would do in this case. Iron 3 oxide is Fe2O3. We know that. How do we know that? Because oxygen is a 2- charge, which means 6- total. And if this is going to be 6+ to balance these two, this 6-, then each one of those iron has to be a 3+. No other way. It can't happen any other way. So we know that formula is correct. Now that we know the formula, we can use it to calculate what's the percent iron in that compound. What we need to know is the total plus what's the iron. How much iron is in that set? So what we would need was the molar mass of the compound. Right? So we would need 2 irons, which is what? 5585. 55.85 grams per mole. And we have 2 moles actually per unit or per formula unit. And so that is a value. And then we have, for that same molecule, we have 3 oxygens. Okay, so 5585 times 2 is 111.70. Actually 0.7. So that's grams per unit. Formula units, what I mean. And then this one is 48 grams per unit. So the total is 7, 9, 5, 1. 159.7 grams in that total formula unit. 159.7 grams. And then how much iron is there? Well, we did the calculation already. 111.7 times 100. Is 69.9%. Let's see, I got 4 significant figures, don't I? 94. 69.94%. Okay. That's the percent iron in this compound, theoretically. If you have 100% pure compound, that's what it would be. Okay. Now, if you haven't thought of it already, we should be able to take percent composition information and determine the formula unit. Go backwards, right? And that's what analytical chemists do all the time. They take pure compounds and they go into the lab and they determine the percent composition of each element. And then they use that information plus a little bit of extra information that I'll tell you about in a minute to determine what's the formula of that compound. So it's not all theoretical. I mean, we've been doing theoretical up to now, just balancing charges, things like that, naming compounds. But that's not the way it was done originally. You go into the lab and actually muscle your way through it, find out what the percentage is. All right. So in order to do this one, from highest to lowest percent oxygen by mass, out of lecture time, we would set up Henry Ford again. And we would calculate the percentage oxygen by mass using that same method for each one of these compounds. So it's going to have a different calculation, right? A different total here, a different total there, different total there, total there, and a different number of oxygen. So you're going to have 16 oxygen here, 16 there, 32 there, 32 there, divided by whatever the molar mass is for each compound times 100, and then rank them. Right? And if we did that, if we had time to do it, we would end up with this ratio. Again, percent oxygen by mass is greatest for water, and that makes sense. Even though water is a relatively light compound, 18 grams per mole, by percentage, it's mostly oxygen. So it should be the greatest, should be the largest. Okay. Now I am going to take time to describe this. This is extremely important. This is the way we take percent composition and determine the formula the molecular formula for a compound. First, well, we go through stages. Right? We're given percent by mass of each of the elements in the compound. That's given information. We take that and we determine first the empirical formula. That is, what is the simplest whole number ratio of atoms in the compound? So what do I mean by that? Well, let me use examples. How about the formula for benzene? Is C6H6. The formula for acetylene is C2H2. What's the simplest whole number ratio for each of those compounds? Well, you have to be able to divide the number into their subscripts. Right? If this were C6H5, you're stuck. You can't divide 5 whole number of times into 6. Right? But 6 and 6, you can divide 6 into that. So the empirical formula here is CH. And the divisor was 6. Right? Okay. So that has an empirical formula of CH, simplest whole number ratio. How about this one? Divide through by 2. They both got the same empirical formula. So what good is that going to do? If you can determine the empirical formula of this one or that one, and it's the same value. Well, as is, it's not going to help you. But if you're actually given by an alternate means the actual molar mass of the compound, then you would find that the molar mass here would be greater than this one by about 3 times. Then you could use that to deduce what does this actually represent as the molecular formula. What does this actually represent as the molecular formula? Because they're different compounds. We know that. We don't have to look at this. We can tell benzene smells a certain way, acetylene smells a certain way, and they react differently when they combust. Okay, so that's the empirical formula. Now, how do we get the molecular formula? Well, remember, the divisor here was 6, and the divisor here was 2. Right? So if we propagate this back through, 6 times 1 is 6, and 6 times 1 is 6. That equals this. This one, 2 of these and 2 of those gives you that. So, what would be the empirical weight, the molar mass of this formula unit? It would be 12.01 plus 1.01. Or 13.02 for both of them. This is what I call the empirical weight. But if we multiply this times 6, right, that's this unit right here. If we multiply it by 6, we'll get what? We'll get 12 there and 18 here and 1 is 78. And over here, we have to multiply it by 2. 406.2, 2604. They have different molar masses for their molecular formulas. Even though they have the same empirical weight, these are the molar masses. Right here and here. So if we can find some way to determine the molar mass of each one, we can differentiate between the two. Notice, if you know this for that and this for that, what if you ratio this one divided by 13.02 and divide this one by 13.02? What do you get? You get the multiplier. So if we can determine the empirical formula and its empirical weight, and then we're given the actual molecular weight, the molar mass, then all you have to do is ratio the two, and you got your multiplier. Right here. That's where I'm headed with this problem solution. Okay? So let me show you what you have to do to get there. Well, you don't have to do it this way, but I've tried several ways, and this seems to be the best. Okay. Well, this is what's known as combustion chain. You drive oxygen through your sample, and it's usually an organic sample. And it's combusted with all this extra oxygen in this furnace, and it produces carbon dioxide and water, and extra oxygen and some other gases. You absorb the water with magnesium perchlorate. Sucks it up like a sponge. And you know the weight before, and then you just take it apart and weigh it afterwards. I've done this before, it works. And then you keep the gases going through here, and you pick up the CO2 over here, and do the same thing, weigh before and after. In this case, we pick it up with sodium hydroxide. Now, how much oxygen do you have there? Well, you can't tell from absorbing because you flushed the thing with oxygen, so that's out. Any oxygen that came out of here is going to be overwhelmed by that oxygen. But if you know that your compound is carbon, hydrogen, oxygen only, then by difference, you know how much the sample weighed beforehand, you know how much this is and how much that is. You can determine the carbon from this one and the hydrogen from this one. Then you subtract those from the mass here, and you know how much oxygen is there. If you've got any other elements in there you know of, then you need different absorbers out here to pick those up too. All right, so here we have a compound, adipic acid. And we know it has carbon, hydrogen, oxygen only. A qualitative analysis has been done and determined that those are the only three elements. Then a quantitative analysis was done to determine the actual percentage of each one, probably using that combustion chain. All right, so we have 49.3% carbon. Okay, and we have 6.9% hydrogen. And the rest is oxygen, 43.8. Now, if there's no error here, you should be able to add all those three up and get what number? 100. But we've got to find out, what do you need to know for the empirical formula? We're talking about atom ratios. This is not even mass, right? Percent is a dimensionless number. It simply says parts per 100. So how many, what parts per 100? You don't know. That's the danger of percent. If you don't know what it was derived from, percent means nothing. So that's why we say, usually when we say percent, we'll say mass, or mass, volume, or volume. It gives you at least a clue as to how it was calculated. But in this case, it's mass by mass. So this means grams per 100 grams. All right. So we've got to determine the number of atoms of each empirical formula. Number of atoms in the empirical formula. But we got to find a way to convert that to grams. Because how are we going to get the number of atoms? The only relationship we know is molar mass of each of the elements. So we've got to convert this into grams so we can use molar mass. Well, if it's grams per 100 grams, why don't we just say our sample is 100 grams? If our sample is a 100 gram sample, that means this is 49.3 grams, right? Grams per 100 grams. And this one is 6.9 grams. And this one is 43.8 grams. Now we're off to the races. Now Henry Ford jumps in again. We got to get rid of grams. denominator, numerator, and we need the number of moles. So 1 mole of each one has a different mass. Carbon is 12.01, right? Hydrogen is 1.01, oxygen is 16. Okay. That gives us moles. Okay. So we're going to have to do this calculation before we can follow along and finish up, because we're looking for whole number ratios. And I guarantee none of those are going to be whole numbers. So we need to do this calculation first. We can't string it together like some conversion factor. So 49.3 divided by 12.01 is 4. Is that right? Yeah. 4.105. 4.105 moles. Did I do that right? 49.3 carbon. Yeah, okay. And this one is 6.9 divided by 1.01, which is 6.832. And this one is 43.8 divided by 16. 2.738. 2.738. That's how many moles of each element. And this ratio is the simplest ratio already, except it's not whole number. So we gotta squeeze whole number out of it. But this ratio is fixed. That ratio to that ratio to that will not change. Mathematically, we can change it, right? With a ratio, if you multiply all these through by the same factor, it's the same ratio. If you divide them all through by the same factor, it's the same ratio. Right? Learn that in math class, I hope. So how are we going to treat this? The simplest way is to take the smallest number and divide the whole thing through by that small number. Right? If we divide it through by this one, 2.738. Well, this one's obvious. That's 1. 6.832 divided by 2.738 is 2.495. 2.45. And 4.105 divided by 2.738 is 1.499. Okay. At this point, we have to recognize that estimation, as long as it's really close to the nearest value, is okay. Because you can't have ratios of fractional atoms. So we got to take into consideration the fact that these are experimental numbers. There's going to be error in them. So what are these close to? Well, it's obviously 1. This one's very close to 2.5, isn't it? This one's close to 1.5. Okay. That makes the solution a little easier. So now, can we get rid of that half? How do you get rid of the half of a number? Multiply by 2. If we multiply everything by 2, this one becomes 3, this one becomes 5, and this one becomes 2. So there's our ratio, simplest whole number ratio, and you look at the numbers. You can't divide these through by any number and make them simpler. That's the simplest number. So carbon, 3, hydrogen, 5, and oxygen, 2 is the empirical formula. Now, you need another piece of information that just so happens we're given. This is the actual molar mass of the compound. And there are a number of ways you can do this. Most of them involve colligative properties. That's second semester. But in a nutshell, colligative property is some property of a not a particular compound, actually. It's property of matter that changes regularly with some other factor. And it doesn't matter what the compound is. It doesn't matter what the element is. It just matters how many of them there are. So that's how we squeeze out the mass per mole, because it only matters how many moles you have, not what they weigh. Okay, so we're given 146 grams per mole of the actual compound. So what does that mean? Well, that means we've got a multiplier here. And that multiplier will lead us to 146 grams per mole. But what's the empirical weight of this compound right here? Of this formula? What's the formula weight here? Well, let's see. 3 carbons is 36.03. And then 5.05 for the hydrogens. And then 32 for the oxygens. 73.08. Grams per mole of this formula unit. Right? So what if we multiply that by 2 or 1, we only get 73. That's not it. If we multiply by 2, we get 146.16. Bingo. X equals 2. So now the molecular formula is actually C6H10O4. Okay. That's how it's done. You ever seen the movie Young Frankenstein? It's been around for a long time, maybe back in the 80s. It's a typical Mel Brooks slapstick comedy. But in Frankenstein's castle, his great-grandson showed up there, played by Gene Wilder. And he found his private library, Dr. Frankenstein's private library. And he found this book on the shelf, and it had a title on it. It says, "How I Did It." That's how I did it. Okay? Say again? This one? Yeah. 3 times 12.01 plus 5 times 1.01 plus 2 times 16. That will give you the empirical weight of this formula. Okay. I'm sorry. I had that up fast because I was doing these in my head. 3 times 12.01 is 36.03, 5.05, 32. But that's where it came from. Yep. Does that make glucose? I don't think so. Glucose is C6H12O6. I'm not sure what that is. Well, we know what it is. It's adipic acid. That's a fatty acid. I'm not sure how many carbons it is. It's been a while for me. But it has so many carbons strung out like this with hydrogens all around it. And then on the end, it has a carboxylic acid on it. So we can probably figure it out, right? Just keep adding carbons and hydrogens until you get to that weight. You can determine what it is, because we know the general structure. It's got this hydrophobic end out here, and then the hydrophilic end here. We haven't even talked about that property yet, but that's how soaps work, how detergents work. Most of the stuff that makes your clothes dirty is oily. So in order to get it out of your clothes, you got to dissolve it in something that's has an affinity for oil. That's this end of the molecule right here. But in order to wash it out, you got to have something that has an affinity for water. So that's this end of the molecule. That's how soaps work. Anybody had anatomy and physiology in here? Okay. You know about true fats? They talk about true fats. Sort of a circular yes.
I think I said everything.
Okay. Adipic acid is potentially one of the fatty acids attached to glycerol. And it forms a triglyceride. Triglyceride is the true fat. Right? It has 3 carbons like this. And it has, let's see. This, it has another carbon here, and that. Okay. This is that long tail right there. These fatty acids. So true fats have 3 fatty acids attached to them. And they're attached with these glyceride bonds. Actually, they're esters, but that's neither here nor there. But that's where that adipic acid probably came from. You just bust that molecule up and purify the fatty acid from it. Anybody have any grandparents that still make their own soap? No. Okay. You just take fat, lard, and you add sodium hydroxide to it, lye, and it breaks that bond, and it makes the sodium salt of the acid attached to the acid end, and then the glycerol is left over. That's how it works. Problem is, soaps will actually, calcium and magnesium have a stronger affinity for those fatty acids than sodium does. So if you have calcium and magnesium in your water, like we do around here, it tends to have like a calcium here and a fatty acid strung out this way and a fatty acid strung out this way, and it won't turn loose. So that's where you get the scum that forms on your clothes and in your pipes and everywhere. That's what water softening is all about. If you overwhelm your water supply with sodium, just plain salt, then it'll dislodge that calcium and soften your water. And then it'll wash your clothes better, make your hair cleaner. It'll feel nice and slick. I used to live, like I said, in Baton Rouge, and we had sodium-rich water down there because it's so close to the ocean. And it was great. You wash and you dry off, but you never feel like you're dry because that sodium on you makes you kind of slick. But you get used to it after a while. Anyway, okay, so now there's the empirical formula and there's the molecular formula. All right, so if you're given a formula like this, you know how to make the empirical formula out of it. You look for a divisor that will go into every factor. In this one case, 3 won't work, 2 works. 2 goes in here, 3, 5, and 2. And you can't simplify it any further. That's how you get the empirical formula from a molecular formula. All right. Let's see. Chemical reactions. I'm running way over. When we write a chemical reaction, we always put the reactants on the left-hand side, products on the right-hand side, and the arrow in between. Now, this is an overall reaction. This is what we've determined to happen. When we put these reactants together, we get those products. We're not saying anything about what happens inside that arrow. There's a lot going on in that arrow. But right now, we're not concerned with that. We just want to know reactants and products and what's their relationship to one another. Right? We have 1 mole or Yeah, 1 mole of this or 1 molecule of that. That, by the way, is ethanol, the drinking kind. And then you add oxygen to it. 3 moles of oxygen in 1 mole of this will give you 2 moles of carbon dioxide and 3 moles of water. That is a balanced equation. Now, why is it balanced? Because, well, first of all, according to Lavoisier, the same amount of mass over here is equal to mass over there. Right? But this says why it happens. And this we think we have Dalton to thank for. We're just rearranging atoms. You have the same number of atoms here of each element as you do over there. That's why the mass is equal. Right? So we have 2 carbons here. Look at there. 2 carbons. This, by the way, this number is called a coefficient. And it's placed in front of the compound or the element. And if you want to know how many atoms are actually going into the reaction or coming out, you multiply that coefficient times how many atoms are in the compound. So in this case, we've got 2 oxygens. That means there are 4 oxygens here in that product. And over here, we've got 1 oxygen there and 3 of the molecules. So there are 3 oxygens there. So 3 plus 4 is 7. Do we have that many over here? Well, 2 times 3 is 6. Plus 1 is 7. Yeah, we did. It's balanced for oxygen. We could do the same thing for the other elements. Now, once you've written these compounds correctly, can't touch them. They're sacred. They stay that way here until they get across that arrow, and then there's something else. But when there's something else, you can't touch those either. You can't change the subscripts to balance an equation. That's the moral here. You have to use coefficients only. Because if you change the subscripts, you change the compound. And we've already established that this plus that yields that plus that. Nothing else, just those compounds and elements. So you start messing around with the subscripts, you're messing around with the compounds. And you can't do that. Not unless you write a whole new equation. All right. And I just said all that stuff. The equation's balanced for those reasons. Now, another thing to recognize is this equation that we've written is theoretical. In other words, we're saying that 100% of the reactants come together and make and disappear, and they make 100% of the products. Okay, we got to start somewhere. So we start with easy. And if you think in terms of 100%, then yeah, that's easy. And when we say amount, in this case, amount means number of moles. But sometimes when we say amount, we mean mass. And I'm going to show you how to relate moles and mass in a balanced equation. Okay, first we got to learn how to balance equations, though. If you read your textbook, if you read most chemical textbooks, they will tell you eventually balance the equation by inspection. I always thought that was a cop-out. They didn't want to take the time to show you how to balance. Now, some textbooks do actually show you how to balance equations. And a good chemistry teacher will show you how to do that too. At least get you started. Some are really hair pullers, but I'm not going to give you any of those. They should be able, you should be able to balance them using the method. I use a budget method. And these are some helpful hints, and these are here in black and white, just so you have a record of it. But I'm going to show you how to balance an equation. Let's see, let me pick one. That's too complicated. Let's stick at that for a moment. How about this one? Yeah. Here you go. We're going to start with glucose. Right? We're going to burn glucose. You know you can set glucose on fire. You can set table sugar on fire. Just put it in your teaspoon and light it with a match. It'll burn. But if we take that into our bodies, we don't want to combust it that fast. It'll do tissue damage. So that's why our body breaks it down in steps. And each one of those steps either requires a little energy to get it going to the next step, or it gives up energy, which is what we want. And it converts that energy into some common currency like ATP. Okay, so let's take this one and use a budget method to balance. So we have glucose, C6H12O6 plus oxygen. Notice I left some space here. I'm not going to put the faces here. Sometimes those are important for balancing, but in this case, they're not. It's only if you've got, say, a compound or an element in one phase on one side and a different phase on the other. It might influence the way the reaction is balanced, but I'm not going to throw that one at you. And then that makes carbon dioxide and water. Notice I left gaps in here for my coefficients. All right, first thing I do, and I use the equation written like this as sort of a header of my table. Down this side, I write the elements, carbon, hydrogen, oxygen. Is that all of them? Yep, that's everybody accounted for. Now, on this side, what are we starting with? 6 carbons. Hydrogens, 12 hydrogens. Oxygens, 6, 7, 8. 8 oxygens. These are starting positions. This one you have 1 carbon and hydrogens, 2 hydrogens, right? And 3 oxygens. Now right off you can see problem. First of all, you've got a 1 and a 3 here, odd numbers, and over here they're all evens. Don't panic. Next thing you have to do is decide where are we going to start. Sometimes after you work so many of these, you have sort of an intuition as to where to begin. But eventually, if you write these compounds correctly, by the way, if you don't write those compounds correctly, or the elements correctly, this equation will never balance. I can guarantee that. So you have to be sure that these are written correctly first. And then you go try to balance. So where do we start? Well, if I don't have an intuition, I just start at the top. So carbons, 6 on this side, I want 6 on this side. So I put 6 there. By the way, where am I not going first? I'm not going to the element first. Why? Because the coefficient in front of that element changes only that element. You may need that at the end. Because if you're at the end and you need more of these, and you put something here, you're going to change the hydrogens too. And then you got another round of balancing to go through. So save these till the last. Free elements go last. So this also changes the number of oxygens. So here we have 12 plus 1 is 13. Okay. Now what? Well, how about hydrogens? Let's see, we've got 12 hydrogens on this side, and we want 12 on this side. So put 6 there, and that makes 12 hydrogens, correct? But it also changes the number of oxygens. 12 plus 6 is 18. Okay? Now, notice we got oxygens in 2 different places here. So how many oxygens, if we want this to be our last step, then we don't want to touch this one. So we've already got 6 oxygens there. I mean, 6 from 18 is 12, right? So we really only need 12 more oxygens. So if I put a 6 here, that gives me 12 oxygens. And 12 plus 6 is 18. And the beauty of this budgeting system is you can instantly see that you're balanced. 6, 6, 12, 12, 18, 18. Okay. That was a simple example. There are a couple of tricks, actually helpful hints. If you have, it's also helpful sometimes if you don't have any elements, try to hold water till last 2. It doesn't always work that way, but you can think about it. Suppose you get to the point for this combustion, that's octane in your gas tank. And we're combusting and making carbon dioxide and water. Okay. We've reached the point in our calculation, in our balancing, where we used a fraction. 25 halves gives you how many oxygens? 25. 25 oxygens is what you needed to balance the oxygens on that side. Right? 16 plus 9 is 25. So 25 halves is an intermediate step. You want your coefficients to be whole numbers. But sometimes you can use a fraction as an intermediate step. Now, this equation is technically balanced. But how do we convert it into whole numbers? We got to get rid of that half. So if this is balanced, then if you do something to the entire equation, it's still balanced. You can divide by a whole number, you can multiply by a whole number. In this case, we multiply by 2. 2 times 25 halves is what? 25. Correct? So 2 times that gives you 2 of those. And 2 times that gets rid of the half and gives you 25 of those. 2 times that gives you 16, and 2 times that gives you 18. Now we have whole numbers. And we saved ourselves a lot of work and headache by an intermediate fraction step. Okay. It doesn't have to be halves, right? It just worked out here. Like if we had, I don't know, P4, like phosphorus, then we could say 25 fourths, or whatever the case may be. Take a fourth of that P4 is 1, right? Then times 25 is 25 of it. So it just so happens that these hydrocarbons, anything above methane, you'll always end up with a fraction problem. Methane, ethane, propane, butane, pentane, hexane, all the way up when you combust them with oxygen. They always make carbon dioxide and water, and they always create this fraction problem. Okay, the other trick is if you have an equation with polyatomic ions in it, look to see if the polyatomic retains its identity on both sides of the equation. Here we have ammonia. That's the only place that occurs here. Over here we have ammonia. That's the only place it occurs. It hasn't changed on either side. So in that case, you can use ammonia rather than nitrogen and hydrogen separately as your balancing group. Now, you may have nitrogens elsewhere. You may have hydrogens elsewhere. But as long as you got ammonia here and ammonia there, you can use it as a separate balancing group. And it saves a lot of work to do it that way. Same thing with phosphate, right? There and there. So that's why I set the table up like this. Ammonia, phosphate, calcium, and chlorine. Right? We can go through each step. Right? That's initial amounts. And then the first one I want to go to is calcium. Yeah, calcium. 3 calciums make 6 chlorines. Right? So we have to change that. 3 calciums, and 6 chlorines. Okay. So now, where do I go? Well, the next step, I want to change the chlorines on the product side to match the chlorines on this side. So I'm going to put a 6 in front of that one. So now what does that do? Well, that changes my ammonias also. And now I need to change the ammonias, right, to 6. So 2 times this, how does that 6? 3 here times 2 there is 6. 6 ammonias. Okay, so we keep tallying those guys. And look, 6, 6, 2, 2, 3, 3, 6, 6. We're balanced. Oh, there we go. Now we're pretty balanced. Blues all around. Okay. This just makes the point that technically these 3 are balanced equations. That one's not. Right. They're all balanced equations, but only one is the preferred, right? The simplest whole number, which is Roman numeral 2. Okay. I'm just hammering these ideas into you, especially subscripts cannot be changed to balance an equation. So how do we do stoichiometric calculations? What do we mean by stoichiometric? We mean that when we count the atoms to balance an equation, we're also counting masses, right? Because each atom weighs something. You can use that relationship to say, all right, if so many grams of glucose goes in this side, how much carbon dioxide will come out the other side? If I take so many grams of carbon dioxide or glucose into my system, which is the primary energy source, particularly for the brain, how much carbon dioxide will I exhale? Right? And you can do that calculation. So first of all, you need a balanced equation. And then, I'm not going to use that. That's too confusing. Let's just do an example about that. And this one has been balanced already. So they went through the same procedure, or they did it by inspection. And we have P4 solid and 5 moles of oxygen gas yields what? Yields 2 P2O5 solid. Okay, so we're going to burn phosphorus. By the way, this is a violent exothermic reaction. That's why they put it in match heads. But that's a balanced equation. And if we say, all right, 6.25 grams of phosphorus, 6.25 grams of phosphorus is burned, what mass of oxygen does it combine with? So what are we saying? We're saying that there's plenty of oxygen. We're going to use all this up and however much oxygen it takes. We want to know how much oxygen does it take. Right? So that's our unknown right there. In mass, the problem is this equation is balanced for numbers of atoms, moles of atoms, molecules. It's not balanced for mass. So think of it as once you have a balanced equation, there's a great wall here and here. Anywhere there's separate components, you got a great wall. You can't get over that wall. You can't go under it unless you're moles. If you're moles, sky's the limit. You just hop right over it. So this grams can't go anywhere until we convert it to moles. So P4, how do we convert 6.25 to P4 moles? Right, that's your conversion factor. Get rid of grams, leaves you with moles. When you see grams and moles in a quotient, instantly think molar mass. What's the molar mass of P4? Well, it's just 4 phosphorus. Right? So you look on your chart, phosphorus is 30.97 times 4 of them, right? 38, 3. Well, 123.88. 123.88. I can't do that one in my head, so I guess I'll have to use my calculator. 6.25 grams divided by 123.88. So that's 5.045. I'm keeping an extra decimal here. I do that a lot. Times 10, excuse me, times 10 to the minus 2 moles of what? P4. That's how many moles you got right there. So how many moles of oxygen is it going to take? Well, the ratio is for every one of these takes 5 of those. And this is the moles of those. This is the moles of P4. 1 mole of P4 is related to oxygen by the coefficient. There you go. So now we can find out how many moles of oxygen is required simply by the balanced equation. These coefficients give you conversion factors. In this case, you can have a conversion factor from here to here, or from here to here, or you can go from here to here, or here to here, or you can go from here to here, or here to here. You got a bunch of different conversion factors, all from the coefficients. That cancels this one and leaves you with moles of oxygen. So I just need 5 times, still in my calculator? Yeah, 5 times that number. 2.52 times 10 to the minus 1. 2.52 times 10 to the minus 1 moles of O2. That's important. It's not O, it's O2. Because this coefficient is in front of O2, not in front of O. Now, what was the question again? Mass of oxygen. I always have to go back to the question and keep myself from, as my dad would say, jump on my horse and ride off in every direction. So we're going to convert this to grams. So we're getting rid of moles and leave us with grams. So how many grams per mole of O2? 32. 16 times 2. There you go. So 32 times that value, which is still in my calculator, is 8.07 grams. 8.07 grams of O2 will be required to consume all of this P4. That's the general layout of all stoichiometric problems. Right? Whatever you have here, if it's not moles, you got to find a way to make it moles. Otherwise, you're stuck. You can't go anywhere. Okay? That's because of the nature of the balanced equation. It's always in terms of numbers of atoms and numbers of molecules. Moles, moles, moles. So if you have a solution here with a concentration, then you've got to know what's the volume of the solution that you're using. And that usually will give you the number of moles. We'll have examples of that later. Always think in terms of moles. If you want to get over this great wall, you better be moles. Right? Gas is too heavy. It won't fly. And it's too weak. You can't dig underneath. Got to be moles. Okay. I've been keeping up with my hard copy. Let me see how much more we got to go. Limiting reactants. I think that's the last topic. I'm already an hour over. That's the way I operate. Okay. We're not going to spend a lot of time on this one because it just takes too long. But it's here, and if you really want a detailed explanation, just look at last semester. I think I did one for that. What we're saying here is that if we react methane with oxygen and air to produce carbon dioxide and water, which means what? A word problem that has to be converted into a balanced equation. Reactants, methane, I can give you the formula for methane, react with oxygen in the air. So what is it going to be? O2, diatomic, and hydrogen. Those are all diatomic. Ammonia reacts with oxygen in the air, same diatomic oxygen, different reaction. This one produces carbon dioxide and water. This one produces nitrogen monoxide and water. So those are two separate reactions, but we're going to relate them. Once you have these balanced equations, here we go. There's a balanced equation for that one. Here's a balanced equation for that one. Ammonia, oxygen, nitrogen monoxide, and water. And then we want to know what mass of ammonia will produce the same amount of water as 1 gram of methane. So if we look at those equations, we want to know how much of this will it take to produce the same amount of water mass as 1 gram of this. So this one's going to react down there and produce some here. This one's going to react and produce some there. We want both of those to be exactly equal. Okay, that's the connection between these two equations. They're not physically connected. They're connected only by the problem. So you need the balanced equations, right? Then you need to say, okay, if I've got 1 gram of this, how much water will I have? If I combust this completely, how much water will it give me? Well, that's how many moles of methane you have. Then we convert it with using this relationship here, 2 to 1, to give you that many moles of water. Okay, if you have that many moles of water, do you have the same mass? Will it answer the question? Yes. The number of moles is all you need. You don't need the number. You don't need the mass. Right? This number of moles is the same as the moles here. And then you work backwards to give you the amount of ammonia. So here we have this many moles of water, this many moles of water. We're going to use a conversion factor to get rid of water, 6 to 4, 6 to 4. So now we know that we need this many moles of ammonia. So just convert it using molar mass of ammonia. And it says you need 1.42 grams of ammonia to produce the same amount of water as 1 gram of methane. Okay. All right. Now limiting reactants. Right. Now, up to this point, we've been in Wonderland. Right. Everything's 100%. In reality, never happens. 100% reaction never happens. If you have 2 reactants or more, you can never measure them exactly, such that they're all consumed and are gone to produce products. That's called the stoichiometric mixture. It's purely theoretical, but we got to start somewhere. In reality, even if you use the most accurate balances, there's going to be enough error in there that one of them is going to run out first. That's the limiting reactant. What happens when that reactant runs out? The reaction stops. Sometimes, once you've identified the reaction that you're experimenting with, you want to be sure that this reactant is completely consumed. So you guarantee that it's the limiting reactant. You put in excess of something else, and then you know it's gone. For instance, we're going to do one of those, I think, when we get to thermochemistry. We have an acid reacting with a base, which is exothermic reaction that produces heat. But we want to be sure that one of the reactants, the reaction goes to completion. And in order for the reactant to go to completion, we have to guarantee that one of them is limiting and one of them is excess. So we do that and we set up the experiment. All right. So this is the artist's idea of a stoichiometric mixture, right? For this reaction, you need 1 mole of nitrogen and 3 moles of hydrogen. So there's 1 to 3, 1 to 3, 1 to 3. That's a stoichiometric mixture. It produces 2 moles each. Each one of these dotted lines produces 2 moles of ammonia. That's stoichiometric. This one's limiting. So which one's limiting? Well, sometimes it's easier to look for the excess, right? Here's the excess, right? These two are still over here. So what's the other one? The other one's hydrogen. Hydrogen is limiting. It doesn't have enough dance partners to go around. So it runs out. Okay. Which one of these produces the greatest amount of product if it involves this reaction? 2 moles of hydrogen and 2 moles of oxygen. 2 moles of hydrogen, 2 of these, but the ratio is 2 to 1. So which one's going to run out first? Hydrogen. You've got excess oxygen. And it produces 2 moles of water. So 2 moles of water, oops, give the answer away. 2 moles of water for this one. How about this one? 2 plus 3, same deal. Hydrogen runs out first. You can only produce 2 moles of water. How about this one? 2 moles of hydrogen and 1 mole of oxygen. Well, which one runs out first this time? Actually, that's stoichiometric. 2 to 1 makes 2. So this one makes the same amount as that one, How about this one? 3 moles of hydrogen, 1 mole of oxygen. Oxygen runs out first, but the ratio is 1 to 2. So with 1 mole of oxygen, you get 2 moles of water, same. That's why the answer is each one produces the same amount of product. All right. It's not a simple road to travel to find out the limiting reactant. What you have to do is you have to calculate the number of moles of each of the reactants. And then you treat each reactant as if it is completely consumed to produce product. And then you look at the amount of product that each one produces. And the one that produces the least amount of product is the limiting reactant. Probably need an example. Okay, let's see. Oops, no example. Must be some in the review document. All right. Now we're going to have to pass on that. Try them in the review document, see if you have any success. If not, we'll cover it. What is today? We'll cover it on Thursday. But you also need to know percent yield, because in the real world, accidents happen. Spills, incomplete reactions, the reactor is dirty, side reactions that steal your reactants and send them someplace else. So in reality, you have a certain amount of yield of a product, and you can compare that to what the theoretical yield, because you know what you started with, and stoichiometrically speaking, you know what you should end up with. But when you actually measure it, it's always less. And you just ratio those two times 100, and that's your percent yield. Okay? Let's see. We got this does give us some limiting reactant experience. So let's work this problem. So here's the reaction. We got P4 plus fluorine, I believe, 6 fluorine, which is diatomic, yields what? 4 PF3 gas. The question is, what mass of P4 is needed to produce 85 grams of PF3? Well, if it was 100% efficient, that'd be simple. We just put 85 grams. And then we do our molar calculations and find out how much. Problem is, there's an efficiency with this. There's a yield factor of 64.9%. So if you do it that way, then 64.9% of that is all you're going to end up with, and it'll be less than 85. So you have to say, all right, theoretically speaking, how much would this have to be, theoretically, to produce the amount that I want? So what we need to do is modify this one so that it will give us the our new starting position. Let's see, did I put it in? Yeah. So our new starting position will be 130.97 grams. There we go. That's PF3. That's where we need to start with our stoichiometry, to go back to here. Because if we find out how much theoretically to produce that, then with this efficiency built in, this yield built in, now we're going to end up with what we need. But this one doesn't give us a limiting reactant. Sorry. It only talks about yield. And we're saying that we've got plenty of fluorine. We could make this the limiting reactant, or could make this the limiting reactant. In fact, if this is excess, this is automatically limited. They come in pairs like that. Actually, there's only one limit. If you have one or more other reactants, they're all excess. But you could theoretically figure this one runs out first, which one runs out second if you had more of this. So I'm chasing the rabbit down that hole. Let's get back on surface and finish this problem. So we use this as our starting position. So now we have to convert that to moles here so that we can get it back over to here. So we need the molar mass of PF3, which means 1.489 moles of PF3. And then we convert that with this ratio of 4 to 1. There it is. Cancels the PF3 and leaves us with P4. And that's how many moles of P4. Then we convert it back to mass using its molar mass. 46.1 grams. If you start out with 46.1 grams here, you will end up with 85 grams here with this yield efficiency. And chemical engineers keep their jobs. One of the ways they keep their jobs is by improving efficiency in the manufacturing process. If they can keep doing that, in addition to creating new processes, of course, but if they can improve the efficiency of the existing processes, that's more money in the company's coffers, and they get to keep their jobs.